question here. So from this example, we know the sine function, sine x, are eigenfunctions of this particular Differential problem. Okay. How about cosine function? Well, we can have another example. So this time we have, if we are using different boundary condition. Now we are using different boundary condition here. Okay. So now we have the ODE is the same as previous one, but the boundary condition are changed. Okay, so we have two different boundary conditions. All right, and in this case, so the data changed here. Okay, we have changed the data about the boundary conditions. Okay. And once again, the general solution, right? The general solution, we obtain the general solution independent of the boundary conditions. So the lambda is negative. Now, so we have to change that y prime. So for y prime, we have mu c1 minus c2. Okay? Because when we take the derivative with respect to x, we have mu here, minus mu here. So we have here, and we have mu c1 e mu, okay, minus c2 pi equal to 0. Okay. Okay, and now we can eliminate the mu because mu is positive. Okay, so we can eliminate mu, and so we have the minus here and the minus here. And once again, this matrix is also non-singular, right? Even I change, this is minus 1, minus here. Okay, it is still non-singular. So we have trivial solution on it. For here, we have because the derivative is equal to C2, so this is C2 equal to 0. Okay, and y prime, okay, y prime. So y prime says that we have C2 equal to 0. Right? So for lambda equal to 0, we require C2 equal to 0. So C1 can be non-zero. So we have a non-trivial solution. Y of x is equal to 1. Right? So now we have a non-trivial solution 1, right? Because C1 is not equal to 0. Okay. That's 1 is eigenfunction corresponding to eigenvalue lambda equal to 0. Okay, so 0 is an eigenvalue, and the corresponding eigenfunction is a constant one. Okay, so we have modified it because we changed the boundary condition. Okay. Now the third In such case, the lambda is positive here. So this is a general solution. And so y prime, when y prime here, because you know y prime x is equal to minus mu a sine mu x plus mu b cosine the mu x. This is y prime, right? So y0 implies that b mu b is 0, so implies b is 0. So now b is 0. Okay? And y prime I. So b is 0. So we have only this term. And so pi, so we have minus a sine mu pi equal to 0. Okay? Now, to have a non-trivial solution, namely, we want a not equal to 0, because b must be 0 from the boundary condition. So, to have a non-trivial solution means a not equal to 0 must have, again, sine mu pi equal to 0. Again. Okay? Again. And so mu must be an integer because mu is greater than 0. So we have eigenvalues number equal to n squared with corresponding eigenfunctions which are cosine. Okay? Because a is non-zero, so we have cosine. Okay? So for this example, eigenvalues are 0, 1, 4, 9, 16, 25, 36, etc. Right? And corresponding eigenfunctions are constant, are 1, our cosine the nx. Okay? Any questions? For the second example. Okay. Well, now we will go to general theory because we are given two examples, right? To illustrate that our trigonometric system are special cases of our student real problem. Okay, so now we let Okay, so we let V be the vector space of all secondary differentiable. Means that the function f of x has a second derivative on AB and satisfying the two boundary conditions in 11.5.2. And you can verify that this space, this set is actually a vector space because you can add two functions. If you add two functions, the sum is also secondary differentiable and it satisfies the two boundary conditions because two boundary conditions are linear. Okay? Okay, so I will not go to the detail. Okay? And your boundary condition, where is the boundary condition? You can, but you always see that. Okay. All right. So we have a vector space. Okay. Well. Now, relate okay, for all. Now we consider an operator, L. So L is an operator on any members or vectors in V. Right? Each vector in V is just a function, right, which is secondary differentiable. Okay, so the L operator on y, the result is that you take the derivative of y, multiply with p of x, and then take the derivative again, and times minus 1, and minus the product of q of x and y. So this is the result. Okay? Thus, the Stern-Liouville equation okay, and it can be shown that L is a linear operator, a linear transformation on V. Okay. Why is linear? Well, if we can see that alpha y1 plus beta y2. Okay? So the operator L operates on the linear combination of y and y2. Okay? So for all y1, y2 in the vector spaces, and for all alpha, beta, real. Now we consider that, so this is minus p of x, alpha y1 plus beta y2 prime, and the prime, minus q of x, alpha y1 plus beta y2. Okay? Here. Now, p of x, because derivative is linear, so we have alpha px y1 prime plus beta p of x y2 prime and prime, and minus alpha q of x y1 minus beta q of x y2. Okay? And once again, the derivative is linear, so we have alpha p of x y1 prime minus beta dx right from. Okay, and now we just combine the first and the third term. So we have alpha minus p of x, 1 from minus qx, 1 plus beta, from Alright, so this is alpha L by 1 plus beta L by 2. Okay, so we prove the linearity, okay, of the operator L. Okay, so it's linear transformation. Okay, so okay, the Differential equation becomes to L y equal to lambda r x y. Okay, so like it down, we can look back to the original Differential equation. You can see that, right? The result, this result is defined to be an operator L on y, and the result should be equal to, this one should be equal to lambda times r x times f times y. Now, okay, all right. So we turn the Differential equation becomes to an equation about the linear operator. Okay, and we have included a function r here. If r is equal to 1, then you have the ordinary eigen equation, right? If I is 1, then Ly equal to lambda 1 means that this is an eigen equation. And any non-trivial solution y is called eigen functions, and then the corresponding lambda is our eigenvalues. Okay? But we can generalize this result by including the Rx here. Okay. So it is a kind of an eigen equation. Okay. Of the Differential linear operator, linear transformation. Yeah. Okay. So this is a kind of eigen equations here. And we want to solve this eigen equation. Okay. So any non-trivial solution is called eigen functions, and the corresponding lambda are called eigenvalues. Okay. So that is the reason why we call them eigenfunctions, eigenvalues. So any questions? Now, for any u v in the vector space, Okay, so now we consider any two functions uv in the vector space V here. So remember, u and v is in here. So u and v are secondary differentiable functions and satisfying the two boundary conditions. Remember that, okay? So u, v are two functions. Okay, so by definition, this is equal to minus p q from minus q u and v here. Okay, the u by our definition is here minus p u from minus q times u and times v. Okay, so we have two terms. We have minus ab and p u from v dx minus ab q u v dx. Okay, so we have that. So now, for this one, we think about the equation by parts. So think about here, minus. So we have p u from dx. Okay, so we have v from dx. And we have p u from. Okay. All right. So by integration by parts, we have p u from and v minus dA, okay, plus AB and P U from and V from dx, okay, and the minus Q U V dx. Okay. Now for here, we do the integration by parts again. So we have p u from dx, okay, p u from dx. So we have p u from dx, and here is u, okay, here. So once again, we have p u from v dA, okay, so here plus p u from v, okay, here, okay, and the minus p u from v dx, okay, all right, and the minus u v dx, okay. So now we have p minus p over x, okay, and u from x dx minus ux u from x dA, okay, plus ab. So So we have U here, okay, and L with dx. We combine this together, or we just break down. U here and minus P minus Q here. Okay? Alright. So now we substitute. For here we have minus PB. Okay? And we have U from B with B minus UB and V from B. Okay, plus alright. So, and now if we compute also minus Px U from X dx dA. So now the first term, we now compute the first term, PB, U from B, and VB minus UB, V from B. Okay, plus PA, U from A, VA, minus UA, V from A. Okay. Right. This is equal to 0. Okay. This is equal to 0. Okay. Since okay, K1 UA plus K2 U from A equal to 0, K1 VA plus K2 U from A equal to 0 means that UA U from A VA, U from A, K1, K2. Okay. This is system of linear equations, right? And we know that here here, at least one of K1, K2 not equal to 0. So this linear equation, right, matrix equation has non-trivial solution. When they have non-trivial solution, it means that the determinant UA, U from A, VA, V from A, not equal to, must be equal to 0, right? Because this measure must be singular. So the determinant is 0, okay? And this means that UA, V from A, minus V from A, VA, equal to 0, okay? So this is 0. So now this equal to 0. Okay, so we prove this difference is 0. Okay. And also this is 0. Why? Similarly, L1 UB plus L2 U plus B equal to 0. L1 VB plus L2 V from B is 0. You can only if UB, U from B, VB, V from B, L1, L2 equal to 0. Okay, and we know that at least one of L1 is not equal to 0. So this means that the determinant of the matrix is equal to 0. So it's only if UB 2 from B minus 2 from B and VB is equal to 0. Okay. Alright, so this is 0. Okay. So from the boundary conditions that this is 0. Okay. Okay, and of course that for here this part is equal to L. So we start with the integral of the product of LU and V. We end up with an integral of U and LV. Okay. All right, so we prove an important theorem here. Okay. Right, so proof that this is called self-adjoint property. Of L. So the operator is self-adjoint. So you can exchange the operator L. So for here, if we consider this integral, the L operates on V, U, or you can use L to operate on V, and the results are the same. Okay, they are the same results. Okay, this is a fundamental relationship we have. Okay, so from theorem, given point 5.8, we have the following theorem. Given point 5.b, all eigenvalues of the SL problem are real. Okay, so all eigenvalues are real. I will not go to the detail. Actually, this is from the property of self-adjoint property. From the self-adjoint property of the operator L. Okay. Okay, and now Okay, now theorem 11.5.1. If phi1 and phi2 are two eigenfunctions of the Differential problem, corresponding to distinct eigenvalues, number 1 and number 2. Then the product of y1 and y2 and the product is Rx. When integral over a and b is equal to 0. This is for equation. Okay? And the remark with 11.5.6 phi1 and phi2 are called orthogonal, okay, with respect to Rx. Okay? So if Rx is the constant function 1, if Rx is 1, then phi1 and phi2 are orthogonal in ordinary sense. Okay? But for Differential problems that we have to put the R of X here. Okay? All right, so we extend the orthogonality concept, right? So to here we can include a function of X. Now we give a proof of this theorem. Since number 1 and number 2 are real. Okay? Okay? So, and we know not all number 2 are reals. As we show here, all eigenvalues of the Differential problems are real. So phi1 is an eigenfunction corresponding to eigenvalue number 1. So it satisfies this equation. Also, phi2 is an eigenfunction corresponding to eigenvalue number 2. Okay? So, L, phi1. So now, L, phi1, phi2 dx is equal to phi1, L, phi2 dx. Okay? I think I have to say no doubt. And by assumption, we have, okay, because phi1 and phi2 are eigenfunctions corresponding to eigenvalues here. Okay? And the things, we have this identity by theorem, given for A. Okay, so we have we apply here. So we have lambda 1 r x by 1 x equal to lambda 2 equal to lambda 1x by 1, and this is lambda 2 x minus here. Okay? Right? So the identity, this identity is from theorem, different point 5.8. And now we substitute the L of phi 1. L of phi 1 is lambda 1 or phi 1 here. And L of phi 2 is lambda 2 r. Okay? So we establish this identity. And we move this both to here. We have lambda 1 minus lambda 2. Which is equal to 0. But phi 1 and phi 2 are distinct. So this is implies that AB Rx phi 1x phi 2x dx equals 0. Okay, so we get the result. Any questions? This is not equal to 0, right? So this is one. So proof is there. Any questions? All right, so actually we already answered our questions about at the beginning of this section that we extend the concept of orthogonality. Right, so the orthogonality actually is extended to this way, that we put a function Rx here. So the original concept of orthogonality corresponding to Rx equal to 1. Okay? Equal to 1. Right? But for the Stern-Liouville problem, when we put Rx here, we still have orthogonality. Right? So this product, this integral equal to 0. Whenever lambda 1 and lambda 2 corresponding to phi 1 and phi 2 are eigenfunctions corresponding to distinct eigenvalues. Okay? So, and the proof of this fundamental theorem, so this is the orthogonality. It's about the orthogonality of eigenfunctions. If eigenfunctions corresponding to distinct eigenvalues, then these two eigenfunctions are orthogonal with respect to Rx. And the proof is because we have the self-adjoint property of that. Now, a Stern-Liouville problem in 11.5.1 and 11.5.2. So 11.5.1 is the Sting-Liouville equation. 11.5.2 is the two boundary conditions. Okay. Now, right, an SL problem is for regular. Okay. If P of X, Q of X, P of X, and the P prime X, the derivative of P of X, Q of X, and the R of X are continuous. AB and P of X is 0. Okay. P of X greater than 0. R of X greater than 0 for all X in the closed interval. Right? So we call a Sting-Liouville problem, okay, to be regular. If Px, P prime X, Qx, Rx are continuous on the closed interval, and the P of X, R of X are all positive here, positive, okay, for all X in the closed interval. So now comes with another theorem on C. The eigenvalue, okay, the eigenvalues of a regular Sting-Liouville problem form an infinite increasing sequence. Okay, so lambda 1, this then lambda 2, 3, etc. Okay, so if you have a regular Sting-Liouville problem, if the Sting-Liouville problem is regular, then you are sure that the eigenvalue, you have infinitely many eigenvalues. Okay, and the eigenvalues form an infinite increasing sequence. So lambda 1 less than lambda 2, let's go to there. And the limit n goes to infinity, lambda n is infinite. Okay, so and that is only one linearly independent eigenfunction. Eigenfunction yn corresponding to each eigenvalue lambda. Okay, so regular eigenvalues there, and the two examples we discussed before are regular SL problems. So you can see that eigenvalues increasing going to infinity, right? And each eigenvalue has only one linearly independent eigenfunction. Right? So you can see that this is the situation for eigenfunction. Okay. Any questions? Okay. So if there is no questions, I start here. and I'll see you on Thursday.